Hello, welcome to class. Thursday, April 9th. So a few things. One, obviously you do have tomorrow off, so enjoy your 3-day weekend. Um, yeah, AP test, 5 weeks are coming up. Yeah, the other thing, the grading cycle would normally end today. The district still hasn't officially made a decision about grades. I just went through and dropped some homework grades in a quiz/test grade anyways, so we'll see. Um, just make sure you keep working. I don't know what the district is going to say about grades, but there's a good chance they might say something about pass fail, or you still have to take a final to prove your mastery, but there's still a good chance that this is going to count. So I wouldn't just think, oh, nothing matters and I can stop working. So just keep working. If you have a friend that's kind of not working, encourage them to work, if for nothing else, for self improvement. But I'm pretty sure the district is going to do something that makes you accountable for the work you did or did not do. All right. And then, so that's about things. If you have any questions about grading or anything, feel free to ask me now or to email me later. But yeah, I still don't have a lot of answers on that. So today, if you look under today's assignment, I posted two different assignments. One of them is Coulomb's Law problems. I just put that as additional practice. I'm not actually taking that up for a grade, but I posted that with some answers if you just want some additional practice to feel better about this topic. So you can work through those and check your answers and still ask questions about those. But today we're going to be looking at methods of charging. So we'll look at this one. So we're going to start off methods of charging. I just have a section here for some notes. You'll go through and write the notes, and I'm going to do the majority of this worksheet, and you'll just do probably about the last question and turn that in for a nice, easy grade. All right. So starting off with some notes, we have conductor. So what's an electrical conductor? What does an electrical conductor do? Well, an electrical conductor will conduct, it probably conducts electricity, is going to easily move electricity. But what was electricity? Electricity, we saw from the previous part, is a moving electric charge. So electricity is a moving electric charge. And when we're talking about electric charge, we're really talking about electrons, right? The protons are stuck in the nucleus. Those are really hard. Yeah, so it starts off with notes, and then we'll go through some like simple examples in action. So yeah, you can write it on paper, or you could print this out and write on it. Either way works. So yeah, a conductor easily moves electricity. Electricity is going to be moving electric charges. Again, charged particles, we have electrons and protons, but electrons are the only things that are easy to move, right? Electrons are in the orbital, they're outside the nucleus. It's a lot easier to remove an electron from an atom than it is to remove a proton from an atom. All right, so a conductor moves electricity. These tend to be metals. So B, an insulator. It does not easily move electricity. And then if conductors tend to be metals, insulators tend to be non-metals. And common things you're going to see are things like rubber or plastic. Just think about what is put around electrical cords. It's usually going to be some sort of plastic or rubber. Look at your phone charger, your anything you plug into an outlet. It's going to be non-metal things. And so that's most of what we're going to be looking at. So conductors are going to move the electricity. The electrons are going to move through this thing easily. Insulator, electrons aren't going to want to move through this, so the electrons are going to be stuck in place, kind of static. All right, so then C, we have the types of electrical charge. So we only have the two charged particles we're looking at. We have electrons and we have protons. So electrons are easy to move. So when we're talking about electricity, we're talking about electrons. Easy to move, so this is electricity. So when you flip on a light switch or you plug something in, it's going to be moving electrons through a wire. We're talking about protons. These are stuck in the nucleus. And so that makes them really hard to move. And again, to rip protons out of a nucleus, we need something really strong, like a nuclear reactor, an atomic bomb, a particle collider, black hole. Like you need something really, really strong to pull protons out of a nucleus. So just really, really high energy is needed here. So when we're talking about electricity, we're really talking about moving electrons. And again, electrons are negatively charged and protons positively charged. And so yeah, that kind of gets into D also. So when we're talking about charging, so today we're going to be charging things, giving things an electric charge. So charging, all we can do for this is we're going to add or remove electrons. So when we look at this, we can either add a negative charge to something or take negative charge away from something. So we're adding or removing electrons, and our protons stay stationary. So anytime we're talking about something moving, it's always going to be where do the electrons move to? So the electrons are going to move and it's going to leave protons in place. So I either add electrons and it gets more negative, or I take electrons away and it gets less negative. All right, so then we're getting into our different types of charging. So we have conduction. And so this is by direct contact. So this would be like electricity moving through wires. Or I could just say touch something with charge to something else with charge. So this is directly in contact, moving through a metal, something like that. So conduction is going to be moving charge by direct contact. This is probably the easiest way to charge something. Just think about how many wires you have in your house, electricity lines, things like this. This is the most common thing. And then F, grounding. I'm not going to get into this a whole lot. Normally we would go into a little bit more depth here, but grounding is just going to be making a material neutral. So we have an equal number of electrons and protons. So we're going to make a material neutral by touching it to the earth. So literally, if you've ever seen something dealing with electricity, it says ground. If you have a ground wire, or if you have those 3-prong outlets, the little round one that goes in the bottom, these are all grounds. And the reason they use the word ground, it's literally talking about the Earth itself. So the Earth itself is made up of just an insane number of electrons and protons. So I can put an excess charge on something, but the second I touch it to the Earth is pretty neutral, and it's this giant reservoir of electrons and protons. So if I touch a charged object to the Earth, the charge wants to disappear into the Earth to kind of average out in order to be neutral again. So anytime you see a ground, that ground is trying to return everything back to neutral, trying to equalize the number of electrons and protons. All right? And then G, we're talking about polarization. Now, polarization, you probably know polarized molecules from chemistry, right? You talk about polarized molecule, probably the biggest one you know of is water, right? You have hydrogen, not hydrogen, the big one is the oxygen. So I have an oxygen and two little hydrogens over here. Now, the oxygen has a lot more protons than the hydrogens, right? So the oxygen is going to hoard the electrons over here and keep the electrons here, but the protons over here, the hydrogens, they don't only have one proton, they can't hold onto the electron as much, so the electron gets moved more to the oxygen, so you have a negative side and a positive side, so kind of like a pole, a negative pole, positive pole. So polarization is going to be the separation of charge. So separation of charge, so we're going to have one positive side, and we're going to have one negative side. So again, pole, also like Earth's pole. We have a North Pole, we have a South Pole. So opposite ends of the charge. So we're going to have one side, one charge, the other side is the other charge. And we'll go through how to actually do this. H is induction. Now, induction, there's a lot of really complicated things that we can do for induction. Again, I'm not going to go super in depth to that because it's can get kind of confusing. But induction, just think of kind of the root word, induce. So we're trying to induce a charge. So when I'm doing induction, I'm going to induce a charge. And this is going to be at a distance. So there's going to be no contact because we're at a distance. So if I'm trying to induce a charge at a distance without contact, I'm going to need a force that can act over a distance without needing direct contact. Well, we just saw that force. We saw the electric force. The electric force doesn't have to have the two objects touching. They'll repel even when they're not touching. It's similar to gravity. Gravity is going to pull things down. There's nothing that literally like reaches up and pulls this down. It's just gravity exists and pulls it down at a distance. So here we're going to induce a charge at a distance using that electric force. So this is going to be something like I put a charge close to something, and I put the charge close to something, that electric force pulls, acts at a distance, and forces things to happen. Yeah. All right. That's kind of the basic of these. I'm not going to go super in depth into these. Again, I'm not going to make this, I tend not to do definitions on tests, but more so being able to apply all these. So let's kind of look at these and see what's happening. So let's kind of go through some of these practice examples. And these are all conceptual, not math. So there's going to be a lot of drawing on this. So when we do this, I do want you to draw out the picture. If you aren't able to print this out, I do want you to try to draw the picture of this electroscope. So we have a negatively charged rubber rod is brought close to a metal top of an electroscope. All right, so I have a negatively charged rod here. This is metal, so metal. Can the electrons move freely through the metal, or are they stuck in place? So I really only care about this right here. So I have metal right here, and then I have these two bottom part. These are called leaves. So an electroscope is just a device for measuring electric charge. All right, so it is a metal. So metal is a conductor of electricity. So the electrons can move easily. And again, we're always talking about electrons moving. So it's never going to be the protons moving for this one. I mean, if you go far enough in physics, you might get to a point where you are talking about protons or other charged particles moving. But yeah, that's going to be a lot higher energy than we're going to be dealing with in here. So I bring a negatively charged object here. So like you said, negatively charged. So like charges repel. So because the like charges repel, the electrons are pushed to the bottom. So will the electrons in the metal stay near the rod or move away from the rod? All right, so we see the electrons are getting pushed down into the bottom here, and then that's answering A. So they move away. And we see that's because like charges, negative and negative, repel. All right, and then so this is B right here. B is on the picture itself. So the electrons are pushed away. Only the electrons can move, so the negative gets pushed away. Now, if I push the electrons away down here, first of all, not all of the electrons move. Like we saw in the book, it's going to be a really tiny number of electrons move compared to the total amount of electrons. So not all of the electrons move here. You still have a lot of electrons here, but a portion of the electrons get pushed down here. So if the electrons move down, what happens to the top of this thing? So I push these negative charges down. What am I left with up here? What's the other charged particle that isn't moving? Yeah, so we have protons stuck in place. Can't spell today. Protons stay in place. So because the electrons are pushed away, I end up with positive charges up here. And let's actually draw this inside. So positive charges are stuck up here. And if this started out neutral, I need to have the same number of positives as I drew negatives. So the protons stay stuck in place right there. It's not that the positive gets pulled up here. It's that the positive, the protons were stuck here. The negative got pushed away, so I was left with more positives right here. All right. And then these electrons are pushed here. I have a negative and a negative into what are called leaves. So do those leaves attract or repel? So I have negative charge, negative charge. think you combine the two words together. Attract or repel? Yeah, they well, negative. So the negative and positive will attract, but we're looking at these two right here. Are these two leaves both negative? So leaves are both negative. So like charges are going to repel. So an electroscope can tell you how strong the electric field is. You move a charge next to something, it'll tell you how much charge you have on something based on how far these separate apart. And then you have gravity trying to pull them back down towards each other. So when I put this close, they're going to repel and move away. But when I move the charge away, now my charges in here will equalize, and then gravity will pull the leaves back down. And you can go and calibrate and calculate forces in order to set this up to actually detect an amount of charge. Now, I did forget one thing on the notes. I forgot to write this on there. So HI. I know you don't have an I on the notes, but we'll put this here. So the last thing I wanted to talk about was charging by friction. So charging by friction, this would be like in the winter, you're walking around with like thick socks on carpets. So you're walking around for a long time. What happens when you go and eventually touch a doorknob? So you're like walking around your socks. Yeah, you get shocked. So when we're talking about that, notice the two things, carpet and socks. Those aren't conductors, right? Those aren't metals. Hopefully you're not walking around wearing metal socks. But charging by frictions, we have two insulators rub together. Now, the insulators don't want to move. You're actually not a very good conductor. You're a pretty poor conductor, but enough of the charge can get stuck. Um, the charge doesn't actually move through your body. It stays relatively stuck to where it's at until you touch it. So you're a pretty poor conductor, but good enough to shock you. So yeah, so we rub these two insulators together. Well, insulators, the charge doesn't want to move, but when they rub, you can think every once in a while an electron gets ripped off from the other one. So the two insulators rub together, and we're going to see the electrons get ripped off, and one of those is going to move to the other side just every once in a while. Um, so this is going to be like a sock on carpet. There's another really big place where this happens, where we have a large buildup of static electricity, something that happens naturally. It's like some big natural source of electricity. Lightning. So lightning, we see a lot of air molecules, dust, water molecules, things like that inside of these big thunder clouds. So the air is an insulator, is moving and bumping into itself. Into other air. So as this goes, the air is going bumping around. Every once in a while, an air molecule goes and hits another air molecule. And every once in a while, electrons are a lot easier to strip away. Every once in a while, an electron just gets ripped away and sticks to another one. So this happens all the time in air, but normally there's just not enough of this going on to build up enough of the static charge. But when you talk about thunderclouds, these things can be like, what is it, up to like 10 miles tall or like 15 miles tall? They get really tall. There's a lot of moving, circulating air, high winds, things blowing around, a lot of air molecules bumping into each other. And over time, you're able to build up just a ridiculous amount of static charge inside the cloud itself. But that reached the point where we have so much charge, there's so much electric force, and then it sees a neutral Earth, and the clouds want to ground themselves. And so it eventually reaches a point where air is a really bad conductor, but there's just so much electricity that it doesn't matter anymore, and the lightning moves through the air, and you get lightning. All right. So that's going into number 3. So number 3, I'm sure everyone's done this at some point. You rub a balloon against your hair, and then when you pull it away, the balloon is all staticky and your hair is standing up. And then you go and you put the balloon on the wall, and the balloon sticks to the wall, right? I'm sure the majority of you have seen this or done this yourself. That's a pretty common thing you do as a kid. So we rub the balloon against our hair. It's going to pick up a charge. The balloon tends to pick up a negative charge when it rubs on your hair. But yeah, so we rub a balloon on our hair, and it picks up a negative charge. So the balloon tends to strip electrons away. So how does that go and attach to a wall? Is the wall itself charged? Go touch your wall. If you touch your wall, do you get shocked? Hopefully not. Yeah. If you do touch your wall and you get shocked, you have really serious electrical issues in your house that you really should get fixed, or your house is going to burn down pretty fast. So please get that fixed. So this is charged by friction. The wall itself is not charged, but if I have an uncharged object, uncharged wall, does uncharged mean no charge? Like if something doesn't have a charge on it, does that mean there's no charge at all whatsoever inside of it? It doesn't mean it's not the charge is zero. But there's a keyword, yeah. So there are still charges. There are still electrons and protons, but our net charge is 0 coulombs, or equal positive and negative charge. So again, everything made up of atoms have electrons and protons. So when we're talking about something being uncharged, it's just the net charge is 0 coulombs. We have the same amount of protons and electrons. So when we're talking about the wall, your wall doesn't have a net charge, but it has a lot of molecules with positives and negatives, right? So if I have a negative balloon and I put this close to a wall, well, all of the molecules in the wall, so molecules in the wall. So first of all, what's the charge that moves, electrons or protons? Electrons move, right? Yeah, so electrons move. So electrons, are they getting attracted or repelled by this negatively charged balloon? Well, we have a negative charge. Electrons are negatively charged. So we're going to see the electrons are going to get repelled. So the electrons get repelled. But our protons stay stuck in place. So the protons are staying stuck right there. The electrons are getting pushed over here. So within the molecules in the wall, we're going to see positive charge getting pulled over here, negative charges pushed to the other side, and just probably draw these with equal charges, the same number, otherwise it would have a net charge. So now the molecules themselves are rearranged, so the electrons are pushed to the other side of the molecules, the protons are pulled over here. Now all of a sudden, what do you have? Now that I have a negative and positive charge close together, negative and positive charges do what? Attract. So we're going to see now all of a sudden we have an electric force pulling the balloon towards the wall. So the balloon itself being charged rearranges the charges within the wall itself. And we even see a positive side, negative side. Well, that looks like polarization. So we put the charged balloon next to a wall. Now, the wall is an insulator, so the electrons aren't moving up and down through the wall, but within the actual molecules and atoms of the things that make up your wall, the electrons can move within those. So within the atom itself, electrons are pushed away by the balloon, leaving more protons on the other side. And all of a sudden, these molecules and atoms are polarized, and the balloon can pull towards the wall. And then yeah, that's kind of going through all those. B is the are the balloon and wall oppositely charged or like charged? Um, so in reality, the wall is neutral, so it's not quite opposite or like charge. But we could say when this polarizes, the opposite charge gets pulled close to the balloon. So that's answering A. So B, so the wall is polarized. Therefore, opposite charges are close together. And because of that, now these opposite charges are close together, and now the balloon is attracted to the wall. All right. Now, C wants to know if you have this negatively charged balloon and we put it next to a stream of water, so we have a small stream of water coming out of a faucet, what's going to happen? It says be sure to talk about the properties of water. I already kind of went through this. What's one of the biggest properties of water you know from chemistry? What type of molecule is water? Yeah, water is polar. Again, we have the oxygen right here. We have hydrogens on either side. By the way, that's what makes it polar. I don't know how much you went into it in chemistry, but you have things like carbon dioxide, where you have the carbon in the middle, and then I think it's a double bond, and then we have an oxygen here, and then so we have this symmetric shape for the bond, so carbon dioxide is not polar because it's symmetric. But because the water forms in this really weird way where the hydrogens are both stuck on the same side, this is why water is a polar molecule. And then it's why it allows it to form hydrogen bonds, and that's the whole reason that water floats when it freezes. It becomes less dense. I don't know. Just the whole way this forms is really strange. Like this is water is a really strange molecule. It's weird that this weird molecule is so prevalent on Earth, but that's also why everyone looks for water when we look for alien life, because it's such a weird molecule with weird properties. But yeah. So again, oxygen has a lot more protons. What is oxygen's numbers? Like 16? Or yeah, is this atomic numbers or is it 8? Yeah, I don't know. I forget. But yeah, oxygen has a lot more protons, so it has a lot more protons, so it holds onto those electrons really tightly. It doesn't know how to share. It bullies the hydrogens and takes too many of the electrons. So the hydrogens are stuck with protons, but they barely get those electrons ever, and so they're left over with a positive side. So I put my balloon next to the water faucet, my negatively charged balloon. Which way are my water molecules going to turn when they are next to the balloon? Which side is going to get turned towards the balloon? Is the oxygen side going to get pulled towards the balloon, or the hydrogen side going to get pulled towards the balloon? I'm sure y'all didn't think we'd be going through chemistry today. Chemistry. So which side gets attracted to the balloon? Does the hydrogen side get attracted to the balloon, or does the oxygen side get attracted to the balloon? Yeah, the hydrogen side is positive, so we're going to see this hydrogen side is going to turn this way, because I have positive, negative. This is obviously not drawn to scale. But our water is going to all turn this way. Negative, positive. So now I have a positive and a negative charge, so we're going to see we have an attractive electric force. So we're going to see the electric force is going to be pulling these things towards the balloon. So we're going to end up seeing something like this, where if I put negatively charged balloon next to this, we're going to have a stream of water is going to go down, and the water is going to bend towards the balloon. And you can actually look up a video of this. I meant to do this earlier, but there's a few of these. But yeah, we have a person charging a balloon. And you see the water bending towards the balloon itself when you put the charged balloon next to the water. Kind of like magic. And this one you can try for yourself, as opposed to the sticking things in electrical outlets. Yeah, it's really weird when you see it. It doesn't seem like it should be happening. Over here, I can also look up an electroscope, so you can actually see what I'm talking about from part 2. so scoop around here. But yeah, you have the thing up top here. This is the metal part that we saw that gets polarized that you put the charge next to. And then we have a metal rod that goes down here. And then we have these two electrical leads that just kind of hang from the bottom here. And then, yeah, here we go. They can move over. They're really light, so they can move towards or away from it. So it gets pulled down by gravity. And when I put an electric charge next to it, it's going to get pulled away from it. And so we put the charged object next to it, and we see the leave pushed away. So it repels, and based on the amount it repels, you can tell how much charge there is there. There's actually, it's pretty simple to make at home. If you want bonus points, build an electroscope and email me a video of it. It's not too difficult to make. All right, so we've gone through charging by friction and a charged object next to an object causing things. It can either make things be polarized or it can move things that are polarized. That spaceship is still being... Which spaceship? The extra credit. Yeah, I'll take that whenever you finish it. I'll retroactively give you 100 if you build me that space station. Or, a moon base. I would also take a moon base, but a large moon base. It has to be at the pole. That way I can always get sunlight, though. All right. So now we have these two metal spheres here. The stands they're on are going to be insulated, so these stands at the bottom aren't going to allow charge to go through them. The only place that charge can move is inside the metal sphere itself. So you have a positive rod brought close to one of the metal spheres, so we charge this with a positive charge. We move it next to the metal spheres. Now, when we're looking at these, before I put the charge next to it, again, if I have two uncharged spheres, uncharged, does uncharged mean no charge? Does uncharged mean no charge? No, it doesn't, right? Uncharged means equal number of protons and electrons. So uncharged means we have an equal number of protons and electrons. So when these are just sitting here, I have the same amount of positives and negatives. So I have equal amounts of charges here. All right, so this starts out uncharged. And then now we can get to what the problem is asking. Now I have these two spheres, and I put a positively charged object next to these spheres. All right, so the only object that can move are the electrons. So which way do the electrons move? Are the electrons pulled towards the positive rod, or are they pushed away from the positive? So are the electrons pulled left or pushed right? Yeah, left. So electrons are going to get attracted to the positive charge. So we're going to see electrons are pulled left. So we're going to see a buildup of electrons over here. And because the electrons move left and the protons are stuck in place. So that means I'm going to have more positives over here. And let's try to draw 1, 2, 3, 4, 5 negatives. 1, 2, 3, 4, 5. Let's try to draw the same number of things here. And again, when you actually talk about this, you really should be talking about electrons move over here, protons are stuck in place, so protons are here. But whenever you're drawing these out, you can just imagine negative gets pulled to the positive, positive gets pushed away from the positive. You can think of it that way. But when you actually explain what's happening, you need to realize it's only electrons moving. And then the other thing, it's not even a lot of electrons. It is a absolutely tiny fraction of the electrons that actually move. So it's not every single electron in here moves over there. We still have a lot of electrons all throughout here. It's just I end up with a higher concentration of electrons here and a higher concentration of protons here. If you were going through and actually ripping all the electrons off of these things, it would turn into superheated plasma. So we're talking about like 4,000 degrees Fahrenheit, maybe hotter. Yeah, so if you're actually ripping all the electrons off, you're vaporizing the metal, which is not easy to do. All right, so these charges move apart like this. And what is this process called, where I have a negative side and a positive side? Starts with a P, ends in an polarization. Yeah, so we're making this polar. This is called polarization. I'm polarizing these. I have a negative pole and a positive pole. Then I look at the after part. Now I pull these apart. So I still have my positive here. Now I separate these spheres. I'm still going to have negatives here, positives here. Now let's go a step further. The question doesn't actually ask us this, but let's remove this thing here. So I remove that thing here and move these really far apart. So now I have negatives here, and I have positives here. So I got rid of this positive rod, and I moved these far apart. So now I have a negatively charged object and a positively charged object. Well, I just charged these two objects without touching the object to it. So which type of charging was that? What was that one that we talked about a while ago where we charged something without actually making direct contact? Yeah, this whole process here. If I were to go through this entire process shown here, this whole thing is induction. Now, there's a lot of way to cause induction. This is only one of the possible ways. There's other ways that involve grounding and a lot of different things. I'm not going to go through all of those. But yeah, this is just one of the ways we can induce a charge. Put a charge close to two metal objects, separate the charges, pull the metal objects away so that the charge can no longer move between these because their conduction can't happen. Then I remove this charge. All of a sudden I have a negative charge and a positive charge over here. And so I was able to charge these without actually touching the objects. And there's a lot of uses for induction. There's things called induction motors. It's a little bit different of a concept, but a lot of times you use these things in systems that you don't want to leak. So like nuclear power plants use what are called induction motors. So you don't need to make direct contact with something. You can induce charges, you can induce fields and forces at a distance. That way you can have everything sealed off nice and perfect. That way you don't leak out radiation or things like that. So yeah, induction is rather useful. All right, so B, that was all A was drawing that. B wants to know what is the charge on the right sphere after the separation compared to the left sphere. So if these start out neutral, did I add any charge to the spheres? Overall, did I add charge? I didn't touch any charge to these. Did I like physically put charge on either of the spheres as a whole? If I look at both of these, did I put any charge on these? No. So I started out with no net charge. I still have no net charge, 0 coulombs of net charge. So if I still have no net charge, what has to be true about these two charges? Yeah, they're equal amounts of charge, equal amounts of charge on each sphere. So I could say the negative charge on that left sphere is going to be equal to the amount of positive charge on the right sphere. And we're really just looking at amounts of charge. So however much negative charge I end up on this sphere is equal to the amount of positive charge I had on that sphere. Right, and this is all coming down to, this is another conservation thing, conservation of charge, that we're not creating or destroying charges. So positive and negative charges aren't coming out of nowhere. And again, this is the thing, you could actually create or destroy positive or negative charges, but again, that's talking about nuclear reactions. It's actually more powerful than nuclear reactions. So to consistently create or destroy charges, you would need something more powerful than atomic bombs. So we're not talking about creating or destroying charges here. So the last one I want to work on with you is number 5, and then you'll just do number 6 on your own. I think that's pretty easy homework. And then again, if you want to, you can do the extra Coulomb's law practice. You don't have to show all your work. You can just go type them in your calculator, do them real fast, and see if you get the correct answer. All right. So now we have a little different setup. Now we have a charged metal sphere touched to a neutral wood sphere. Now, negative 4 coulombs, again, 1 coulomb is absolutely massive. You do not want to be near this object. If you go touch that negative 4 coulomb object, it might kill you. So, yeah, that's why we normally deal with micro or nano coulombs. So we have a negative 4 coulomb metal sphere goes and touches a neutral wood sphere, and then I pull them back apart. So what types of materials do we have here? What's the difference between metal and wood? All right, so metal is a conductor, So those electrons can move real easily, but wood is an insulator. So these go, they touch. How much charge is the wood going to pick up when these touch? If wood is an insulator, does it conduct electricity? So an insulator isn't going to conduct electricity. Now, in a perfect world, a perfect insulator, I can't put charge on it this way. In reality, nothing is going to be a perfect insulator. It's the same thing about your body is a really good insulator. But you can still pick up charge, and I can still touch the metal doorknob, and I can still lose charge from my body into the door. It's not going to lose all of it. So it's not going to be a perfect, absolutely nothing can possibly go through this. It's just going to be negligible. So we're going to have a negligible charge transfers to the wood. So when we touch one side of it, yes, this will pick up just the tiniest of tiny charges. If I touch it, I would probably feel statically charged. But it's not going to be taking a lot of the charge. So if this is taking a really, really tiny amount of this 4 coulombs, pretty much none of it, after these two objects touch, the metal is going to end up with the same charge. So the final charge of the metal is going to be still negative 4 coulombs, give or take just the tiniest of tiny amounts of charge that may end up on the very surface of the wood. Yeah, the wood is also going to stay the same. So charge final for the wood is going to be pretty much 0 coulombs. Now, again, when you do touch it, it will probably pick up a small amount. Like if you were to actually measure that point of the wood afterwards, you might pick up like a few nano coulombs, the tiniest of tiny amounts of static charge on that very surface where it touched. But the amount it picks up is going to be so small compared to the amount that the metal itself actually has. And that's more just due to real world effects. So when you actually measure, say, your body, how well your body conducts electricity, well, if you're in like a really dry, cool situation, your body's not going to conduct a lot of electricity. But if you're sweating a lot, you have a bunch of water with electrolytes in that sweat, and you're going to turn into a much better conductor. And so that will change the amount of charge that can actually move across your body. Yeah, so charge isn't going to be moving between the conductor and insulator in any significant amount. So if you have a perfect insulator, then yeah, none of the charge would move. In the real world, you're going to see small amounts again, just due to the fact that it's not going to be an exactly perfect situation. And then one more thing that I probably should go through that I forgot to put on this. Let's just do like one more. Let's call this 5C. Let's just say I have a metal with the same negative 4 coulombs, and then I go and I touch it to another metal that starts at 0 coulombs. And these are the same material, size, and shape. we're not going to get into a whole lot of how those affect things. But let's say same material size and shape, and then I go and I touch these together. How much is each one of these pieces of metal going to get? So -4 here, 0 here. I touch two conductors together. How much does each one of these metal objects get? It will equal. They're each going to get half. So they're going to get -2 coulombs, -2 coulombs, and then I'll go and I'll separate them apart. And then we'll see -2 coulombs here, -2 coulombs here. So we'll see our net charge is going to stay constant, -4 coulombs. So yeah, so if I touch an insulator, the metal is going to keep pretty much everything. Or if I touch two insulators together, they're going to be pretty much the same. But if I touch two equal metal objects, or two conductors, the charge is going to spread across them. And as long as they're identical, they're each going to get half of the charge, or half of that net charge. All right, so the only one that you have to do on your own is number 6. So that shouldn't be too bad. Again, I would suggest you practice the Coulomb's law. I'm just trying not to give y'all too much homework because I know a lot of your classes are stressful, especially the AP classes y'all probably have as you work towards the test. If you're in here and you are taking the AP physics test, I would suggest you at least look through the things I've been posting recently because they're actual AP test questions with rubrics from College Board. So I would look at those, try to work through those, and look at the keys. But other than that, yeah, if you have any questions, ask them now so I can answer them before you go. But yeah, other than that, have a good 3-day weekend. Try to relax a little bit, unwind a little bit from having to do all of these online classes. And grades, again, I don't know exactly how grades are going to work, but I'm just doing everything as if normal and putting things in and dropping grades as if normal. And we'll see when the district actually comes to a decision. There's a good chance they're going to come up with some way to hold you accountable for the things that have been going on here. So hopefully there is some accountability. So if you know someone who isn't doing any work in any of the classes, I would tell them, hey, you should probably at least try. But yeah, other than that, if there's no questions, everyone have a good weekend. And I'll see you, I guess, Monday during tutorials or Tuesday in class.